So hi everyone, and sorry I can't be there. So I'm actually at a meeting in South Africa this week, where I have to be here all week. And so I'm just going to give you a short little talk. It's quite high level. It would have probably actually been a better fit to last week, because what I'm going to talk about briefly is something I don't think that gets talked about in talks very much. And that is, we hear about all these fantastic new surveys and upcoming telescopes and surveys, such as DSA 2000 that you just heard about, as well as Kaustubh's talk with this amazing transient detection system. But there's a huge amount of effort that goes into getting these systems built and tested to make sure that the transients and pulsars and stuff that we get out of these systems, including the software and the hardware, is really what we think they are. And so that takes a huge amount of effort. And because that effort doesn't usually show up in papers, it's students and postdocs usually who are doing this work. It's not something that we think about very often. So that's kind of what this talk is about. And it's really trying to get people to think about continually testing your system to make sure it's really, really doing what you think it is. So if we're doing a transient and pulsation search, and this can be in the past with archival data, it can be with current telescopes, or it can be with future telescopes. This is kind of the high level information that we need and the things that we think about. So for transients in the radio, obviously we need time and frequency resolution. So we tend to have relatively high data volumes for each pixel on the sky. We need to have well-characterized algorithms that find a weak signal in the presence of noise. And normally in radio astronomy, given the radiometer equation and stuff, the noise that we're seeing tends to be Gaussian most of the time. And that noise needs to be well characterized. So if it is Gaussian, we want to know the standard deviation. We want to know, is it relatively constant in amplitude across our spectrum? Is it relatively constant in amplitude as a function of time? And the reason that's important is because for our algorithms that find the signals in those noise, we do statistics. And the statistics is completely based on the tails of distributions. You were looking at the high signal tails of statistical distributions where most of that distribution is described by the noise. And then finally, when we're detecting pulsars or transients, we want to make sure that we're maximizing the number of real, true astrophysical signals, the true positives, while minimizing the number of false positives and false detections that we get from our software and our hardware. And that last thing, minimizing false positives, is something that we also often don't hear about very much. Almost all modern software pipelines find huge numbers of false positives. And so you do hear about machine learning and stuff in ways of sifting through those candidates. But it's a really, really important part of this whole pipeline, is making sure you don't lose the real things and you get rid of as much of the fake, the false positive things as possible. And so how do you do all of these things and make sure this is all working? And the answer is really very careful testing of every different part of your pipeline as often as possible. And it doesn't stop. It's not that you just test in the beginning. You need to be continually checking that your software and your hardware is producing the data that you expect it to provide. So as some examples, I'm going to show you how we've been developing a pipeline for a new search called the CHAMPS survey. This is using the CHIME telescope, and we use the CHIME FRB backend. So that gives us that time and frequency resolution that we need. So roughly 1 millisecond sampling with thousands of frequency channels across our bandwidth. But instead of searching for FRBs, what we're doing is integrating. We've actually changed the way the beams go on the sky so that because CHIME is looking straight up in the sky every single day, it can't tip. It sees the same patch of the sky repetitively each and every day. And so we've changed it so that the beams can track, so that every day a certain rate ascension and declination will get, once it's above CHIME, it gets a beam that tracks for somewhere between 10 and 20 minutes, that source, while the source is within the CHIME's primary beam. From that 10 to 20 minute integration, we now have filter bank data effectively of that whole duration that we can then de-disperse. We can create time series. We can Fourier transform those and make power spectra that we then normalize, make sure we understand the statistics, and then we stack day after day after day. We add power spectra together. And what this allows us to do is very, very deeply and slowly over time integrate up very, very faint pulsing signals. And in general, we can get with the CHIME telescope, which is roughly half the sensitivity of the GDT. If we integrate for, a month or so, we can get to be the most sensitive pulsar survey for isolated pulsars in the northern sky. But yet we can integrate for years if we want or need to, but only if we don't mess up of that from this current survey. And I should mention that the paper on describing the system has just been published, and that's the link at the bottom there, the Andrade et al. Paper. And then just to show you what those figures are on the right, we've already found a few new pulsars at the top up here. Hopefully you can see my cursor. Here's the galactic plane. Here's the whole northern sky. This basically is showing the colors show the expected DM. And then here is a strip that we did some test observations, and we found a bunch of new sources that are these colored points, mostly towards the inner galactic plane, even though this is still far in the north, so it's not really true in the inner galaxy. But it is the galactic plane seen right above CHIME. And then at the bottom, this is just a pulsation sensitivity plot that shows how integrating from a day to a month to a year, and this is a logarithmic scaling on the y-axis that shows how we're able to move down by significant factors if we're able to keep putting these stacks together. All right, so for a stack search, one of the main things that we have is we have time series. We have to take a Fourier transform of the time series and then turn those into power spectra. But some of the things, we make a lot of assumptions about our time series. First off, that in the time domain that we have Gaussian statistics. So this is simulated data, and you're seeing Gaussian random numbers around a mean value of 0 with standard deviation, which is represented by these green lines, that's relatively constant with time. And it's true that a lot of radio data does look like that. But most of you who've seen real radio data know that is definitely not what it all looks like. There's a lot of other stuff in our data. But if you have Gaussian random numbers and you take a Fourier transform, then square those amplitudes to make a power spectra, you get the Fourier domain, which you're seeing here down at the bottom. And the statistics here, because it's power, there's no negatives, and we've squared two Gaussian random numbers to get this, that gives us a chi-square distribution with 2 degrees of freedom. And we know that analytically, it's easy to do that derivation. And we depend on our tests and our looking for our signals on those statistical properties. We depend on that being chi-squared. So one of the big things that I'm advocating is, when you do this, test for Gaussianity of your time domain data, test that your power spectrum data is chi-squared, and not just in general, but even as a function of radio frequency. Similarly, when you inject a sinusoid in your data, and we're looking for pulsations, if we have Gaussian noise and you inject a sinusoid with certain amplitude, you can compute exactly and analytically what the power in that sinusoid should be. And it's theoretically, if you have a perfect system, that sensitivity should be equivalent across your whole pulsation frequency band. So a sinusoid of the same amplitude at 10 hertz should give you the same signal as a sinusoid at 700 hertz, for instance, if we're using normal pulsar style sampling. So we can predict that, and we can test to make sure that that's actually what we're getting. So this is one of the things that we've actually done recently, so I'll talk about some of those things. So de-dispersion is a crucial part of it because this is what prepares our time series. You probably know a lot about de-dispersion now. But for this CHAMPS survey, we're doing huge numbers. We have 1,024 beams on the sky at any one time. We're doing this in real time. So a brute force, which is of order of operations n channels squared, is simply too expensive to do that. So we use some of these new techniques like the FDMT, which is a form of tree dispersion. There's a whole bunch of these tree style codes that turn the operations count into order n log n. But if we think about going from the time domain up here at the top into dispersed time series down here on the bottom, this is a transform. And these software packages do operations on your data. We cannot just trust that what they're doing is all correct. And we actually found an issue with our system that was not found in the software development's testing. So here's an example of that. So what this plot is showing here, it's showing the power that we get out of a sinusoid divided by what we think the power of that sinusoid should be, given that sinusoids should be, we should get the same amplitude out before and after our transformation and at all radio frequencies. And this x-axis down here is logarithmic of basically the frequency that we're looking for pulsations. The Nyquist frequency, so the fastest frequency that we could possibly detect, is right up here basically at this last data point. So it's up at about 500 hertz. And what I want you to see is look at this dashed blue curve right here. It's right here. In general, we would expect this to be completely flat to the very end. But what you can see is that there's a rollover at the top here. And this is something that I think that most pulsar survey papers have actually ignored in the last couple of decades, because that's, I think, something that most people have forgotten. And that is just the fact that we're summing over many channels, and each channel is not perfectly aligned. So we basically choose the nearest sample as we're adding all those things up. Or even if you're using the FDMT, you're basically weighting nearby channels that correlates nearby samples. That means we lose sensitivity at the highest frequencies. And this is the sine power roll-off that we get. It's related to a sinc squared function. And this is in a nice derivation in a paper by Michael van der Klees clear back in 1988 describes this. But the pulsar community's kind of forgotten about this, but our testing brought that back to our attention again. And even worse, we had a very custom implementation in C++ of the FDMT that we had done a bunch of testing with, and it looked all great. And these are the red curves. Notice the red curve precipitously drops off, and this is a log plot. So at factors of about 4 lower frequency, so we would have lost a factor of 4 of our highest frequencies of looking for pulsars, including the higher harmonics, potential millisecond pulsars, things like that, if we hadn't caught this very, very subtle bug in our implementation of the FDMT. And sure enough, this is my student, Ray. They tested a different Python version of the FDMT in this exact same way, and it follows the blue curves, which is just like what Presto's code does. But these are really subtle effects, and we're doing this before the pipeline is fully up and running to make sure that we understand exactly what's going on. I'm getting blinded by the sun, so I'm going to shift over here so I'm not in the sun. Okay. The next little quick example I want to show you is about red noise. Red noise is something that you hear a lot about, especially for now these searches for slower pulsars and long period transients and stuff like that. Almost all real radio data, for all sorts of reasons, tends to have this low frequency correlated component in our data. So our time domain data do not look like pure Gaussian noise. They look like this red noise data, which looks you tend to be dominated by cubics and stuff like that. When you Fourier transform a time series like that, you get, here's your chi-square distribution at the top, but you have incredibly excess power down here at the bottom. Since we're looking for slow pulsars often, this red noise is a true contaminant of your data. You cannot get rid of it. It means you're less sensitive at these lower frequencies. There's no way around it. So the best thing to do is to try to figure out ways to avoid that red noise in the first place. And I mentioned there are some ways to mitigate. For instance, in Presto, there's a routine called red noise, and this was run on that example. You can see from the original power spectra, all this power down here. The corrected power spectrum seems to have gotten rid of that. But these data down here at these low frequencies aren't perfectly chi-square distributed anymore. There's more variance, which means we're going to get more false positives. And we have less sensitivity because the noise was actually larger. So this is an example of something that's very tricky to deal with, and the best thing to do is to try to avoid it in the first place. So Robert Main, a postdoc at McGill, who's working on the CHAMPS project, just did a very deep dive into the way that the correlation is working to generate the chime beams. And we've started to remove the incoherent beam. And Kaustra described about incoherent beams a bit. You probably know this is where you're not using the phases of all the different antennae. You're basically just adding their powers together. But since all of those feeds are detecting the same signal at the same time, you can subtract that from the actual coherent beams, and you can remove a lot of the common mode signal that's seen by all your feeds. So what I'm showing here, this is time frequency data. You can see there's some strong interference. The chime band is quite noisy. But what I want you to see is this vertical striping. There's like some slight yellow green striping. That's the original data. But if I switch back and forth, hopefully this is able to switch fast enough that you can see that those yellow striping, the vertical striping, almost completely goes away. And so that dramatically improves the red noise in our data and makes it significantly more sensitive to really slow pulsars. So that was really excellent work that Robert has done. But RFI, as you can see, was not really affected at all. This narrowband RFI is still a really big issue. That's one of the last things I want to bring up. We know RFI is a huge contaminant to our data, and it's only going to get worse, not better. And it can dramatically change the statistics in your data and gives you huge numbers of false positives. The other thing that's tricky is that with injections, which is one of my last slides I'm going to show about how I recommend to look at a lot of these things, it's very hard to simulate because it's hard to simulate real life RFI. You can do some things, but your simulated RFI is almost always better behaved than real RFI. So one of the things that we normally do is just excise it. So this is a plot from RFI find in Presto, and the red points here just simply get zeroed out effectively in the data processing. And the point what a lot of students often forget about this is that this is often not as bad as you think, because our sensitivity goes as the square root of the bandwidth and the square root of time. So for instance, this example here, where we're having to remove 20% of our band due to the strong interference, given that it's the square root of the bandwidth as our sensitivity, we're only losing about 10% of our overall sensitivity. And then you can also use a bunch of other advantages that RFI is not typically dispersed, and it's the same in simultaneous beams. So kind of as a summary that I want to leave you with, is just about testing this stuff. So I highly recommend people use well-developed and tested codes, and then test and test and test these again. And test for signals, test for noise, and test them quantitatively. You can use pure noise and perfect signals, and you should be able to predict the recovery of your pipelines with pure noise and perfect signals. But then it's even better to test that into real data, because the problem with real data is that there's red noise, there's RFI, stuff like that. And that's why injecting fake signals into real data is one of the very, very best ways to test these pipelines. And you want to inject as close to the beginning of the pipeline as absolutely possible. And it also, what this does is if you do a ton of injections, it also lets you compute as a function of all your different parameter space you're searching over, how efficient your search is going to be. And then the last thing is just make sure, really, please make your code available, put it on GitHub, encourage people to use it, ask them to cite it, which they will, put it on ASCL so you'll get citations, because others use this and they test it and they'll cite you. I see way too much code that people are not sharing nowadays because they've made their new pipeline and they say, oh, my code's not good enough, it's not pretty enough, someday I'll release it. Release it now, make it available, and tell people about it. And then it's just my last slide, just to show you some citations about some of the things I talked about. Here's two amazing papers about how Chime FRB does injections. And if you don't know how this methodology works of injections. It's way beyond this talk. I highly recommend that you look at these two really, really beautiful papers to show how this all works. And keep an eye out for the new CHIME FRB catalog paper. Catalog paper number 2 with over 3,000 FRBs is coming very soon, and a paper on CHAMPS injections by my student Ray. And I'll end there. Thank you.
Thanks very much, Scott. Very nice talk. Questions from the audience? Yeah, question.
Thank you, Scott. I have some point that I think you probably lightly touched upon. So on the scalloping issues, do you want to say something on the final? Yeah, thank you.
Yeah, so scalloping obviously is a very important point for FFT-based searches. The very quick thing for people who don't know what scalloping is, let's say you have 1,024 bins in your time series. If you take the Fourier transform, because of the Nyquist theorem, you get 512 frequencies, but you can have any frequency in your time series. It doesn't have to exactly match one of the 512 bins. So that causes scalloping. Scalloping is something that you have to take into account. And so on average, you're going to lose signal due to scalloping. And so the nice thing about injections, so in the CHIME survey, for the CHIME, the CHAMP survey, our detailed injection pipeline exactly accounts for scalloping in every instance for every harmonic, and it plays a big role. You lose 20 to 40% sensitivity from an FFT-based search due to scalloping. But there are scalloping effects in other algorithms as well. Like it's not completely gone in like even an FFA-based search. It's better, but unless you highly oversample your FFA, which is the fast folding algorithm, you still have scalloping effects even there.
Hey, Scott. Thanks for a really nice talk. I have a question about the plot that you showed where you lose power at the higher frequencies because of dispersion. I saw that there was a little bit of a dip even at the, lower frequencies for some of those plots. Can you explain what that is?
Yeah, this is really quite recent work. I think this just could be just a noise fluctuation because we didn't do for making this particular plot. Ray didn't do a whole ton of injections. But yeah, no, this is interesting. This is something we're looking into. I do not quite understand how the blue lines are dipping right here. And it is at a loss of something like, 10 to 20% over this regime. And this is right in the regime where we're trying to find most of our pulsars. So yeah, we're looking for all of these things. And this is why you really have to test. Like there was no expectation that anything like this should be there. Presto has been tested hugely, and this is using Presto dedispersion. So we're not quite sure exactly. Yeah, so we're looking into it.
Okay, if not, let's thank Scott and the rest of the speakers of the morning session.